Now, to move forward, we have to understand how to make different arity codes from numbers. If you know how to do that, you can just skip this video. So, example of making different arity codes from numbers, it's for example making a binary code from any number, or making a ternary code from some number. Ternary means that our code word alphabet will consist of 3 different letters. In binary this will be 0, 1, and in ternary this can be 0, 1 and 2. And I will teach you how to make any arity code from any number, and how to make from any arity code to recover, how to transform our ternary, binary or whatever code into a number. So, once again, what is a binary code? Binary code is something like that from our previous examples, because it only has 2 different code word letters. This is 0 and 1. Ternary code, consequently, consists of these numbers 0, 1 and 2. Ternary, it means consists from 3. And n-ary, so with n arity, where n can be 4, 5, 10. In 5-ary system we will have letters, code word letters from 1 to 4, not to 5. To 5 it will be 6-ary. Okay, our algorithm will consist of 3 steps. First, we divide our integer, for example 10, by n. N in binary is 2. Or 6 is integer by n. Ternary, in ternary it's 3. Check the remainder. It will become a piece of our code. I think it's clear. And when reached the last number, divide n by number. So this n by number we've got. Produce the remainder. And then at the end we will produce our code. I will show the example right now. Actually, let's use 17, because I found 10 is an easy example. Okay, because we produce the binary code, we on each step divide by 2. And I think the sequence here is very clear. But very important thing here that we produce the code at the end from bottom to top, not from top to bottom, from bottom to top. In this case it's not particularly important because it's palindrome code. Yeah, 0 in the middle. Yeah, let's go to the next example. I will also use a bigger number here. Let's say 77. Now 77 to ternary. 77 divided by 3, it's produced 2. Okay. We can clearly divide 77 by 3. So we divide 77 by n, as in our algorithm definition. And if we do that, we produce 2 full parts and some remainder. This remainder is 2, because if we divide only 75 can be divided by 3 without a remainder. What's the difference between 75 and 77? It's 2, so this is here. Then we divide 25 by 3, then 8, and then 2 by 3. I think it's clear now. And here, this is super simple, 15 divided by 5, because we transform 15 to a 5-ary system. Yeah, maybe here it's not really clear why we've got 3, but in such situation, when number is smaller than n, at the end we produce actually this. This becomes the part of our code. If at the end we would have gotten 4, we would make it. Here would be not a 3 but a 4. This is maybe not very clear part, but that's the way the algorithm works. Let's make one more example to make it absolutely clear. Let's make 5-ary code from 21 to 5-ary. Right? To do that, once again, we divide 21 by 5. It will produce 1 as a reminder, and at the end it will be 4, because 20 divided by 5 is 4. We divide by 5 and produce 4. We produce this number. And once again, as I said, codes are produced from bottom to top. So the code will be 41. Okay, here's the algorithm to transform any fractional number to any arity system. First of all, we multiply our fractional number by n. If it produces an integer part, we subtract this integer part and put it to the code stream. Just add it, concatenate it with the code stream. If not, if there is no integer part, we add 0 to the code stream. We continue until needed, or if 0 is produced. What I mean here, for example, we know that the result of transforming fractional number into some system can produce recursive result, so it will never end. That's why we can continue until we need, like, for example, 5 last symbols. Or if 0 is produced. I will give later an example and you will understand what that means. In the example we will look at binary and ternary codes. We have to multiply but not divide. And often fractional to n array representation produces recursive results. We will never produce an end of the sequence. So, first of all, we determine what is n. n is 2 in our case, and we multiply 1/3 by 2 and produce 2/3. Then we continue with 2/3 and make the same actions. But on each step, if we have produced a number bigger than 1, we have to subtract 1 from the number and add it to the code stream. So let's do it once again. If we multiply 1/3 by 2, it will be 2/3, right? And we produce, actually this is this 0. And we make the following actions, the same actions with 2/3, and we produce number obviously bigger than 1. It will be 4/3. So 4/3 will produce 1, and we will continue working with 1/3, minus 1 here. In ternary we are doing a slightly different thing, but if you can generalize it, it is actually absolutely the same. We multiply by n. n in ternary is 3. It's 3/4. Okay, we work with 3/4 now. 3/4 multiplied by 3 will be 9/4. But what we observe here, number is not only bigger than 1, it's bigger than 2. So we will subtract 2 from here. And at the end it will be 1/4. Right? So the code we produced now is 0, 2. 0, 0, 2 because it's fractional. 0, 2. As I said, result can be recursive, and of course it is recursive here too because we produced 1/4 once again, and we will continue doing it infinitely many times. We can, but we will not. Okay. To make integer from n array code, we have to know n. Without knowing n, we can never do it. Of course, if it's not binary code like this. But it's not the case. Our n now is 5. To make an integer from this strangely looking number in 5 array system, we will have to do the following steps. For each number in the sequence, we have to find the power of 5, which represents each number. Okay, so if it's 0, it will not take part into our following steps. Okay, 5 in third, which represents this one, plus, and we multiply the number in the sequence by the corresponding power of 5, plus 0 multiplied by 2 in power, 5 power of 2, squared 5, plus 4 multiplied by 5 in the first power, plus 3 multiplied by, and at the end we will get, I think it's 225, yes, plus 0, plus 20, plus 3, because this is 1. And this will give us the following result. It will be 248. And it works in any system. Let's work out with binary system. Let's say we have this number, whatever, it can be any number, and we find corresponding powers of 2. 5 and 0 power, first, second, third, fourth, 5 and 5th power. Wait, I mean 2. It will be 2 in some power. I'm sorry. Because n is 2. It will be first, second, third, fourth will not take part. And it will produce some number. It will be 1 plus 2 plus 4 plus 8 plus 32, 40, 46, 47. This will be 47. It works in any arity-system, and the goal once again is to find n, give it power corresponding to the position of the current symbol we are looking at, starting from 0, going from right to left, because numbers are written in such a way that the smallest number is here on the right, and multiply by a number. Okay, here it is a good example. We multiply 3 by 5 in 0 power, 4 by 5 in first power, etc., etc. And we produce our numbers like that. It works in absolutely the same manner with binary numbers, but I will give you an example right now. I'm sorry, I meant not binary, fractional, but fractional. Okay, let's say we have this fractional binary number. We just ignore this part. We ignore it absolutely. And we start from giving, same as in non-fractional manner, we give the powers of 2, but they're in minus powers of 2. The resulting fractional number will be a sum of powers of 2 in minus. 2 minus 3, 2 minus 4. It will be 1/2, 1/4, 1/8, because this is negative powers. 2 minus 2 it will be 1/4. 1/4. It's a negative power. Negative power makes 1 at top, and the power of 2 in numerator will be 1, in denominator will be 4. And 2 in power of in minus 4 it's multiplied by 0. We do not think of it anymore, and it will give us some number. I think it will be 7/8 or whatever. Maybe result may be wrong. I made it very fast, just to make you understand what's happening. The result here 7/8 might be wrong. Yeah. The result of our operations will be this sum. And of course it works in the same, absolutely same manner if we have n bigger than 2. N can be 3, as I said, it will be ternary code, etc. At the end, let's make an example here. We can have such a code. Yeah. And what we will do, we will use a different number other than 2 and make powers of it. N is 3, right? So it will be 3 in minus first, 3 negative second, 3 negative third. But of course, in similar fashion, we have to multiply by these numbers 2. It will be 2 multiplied by 3, 0 multiplied by 3 minus 2, 2 minus 2, and 1 multiplied to 3 negative power 3. And yeah, at the end it will be this sum, 2/3 plus 1/9 multiplied by 0 plus 1 multiplied by I think it's 27. Yeah, and that's it. You can generalize it to any n. At the end, what we do is we multiply each number of the sequence by n in the power which corresponds to the position of our symbol. In fractional, we start from 1. In integers, we'll start from 0. And that's it.